Okay. All right. So we've defined harmonic functions on a Riemannian manifold, those whose Laplacian is 0. And we've also defined, these will also be important, subharmonic and superharmonic functions. So subharmonic functions, the Laplacian is non-negative, and superharmonic functions, the Laplacian is non-positive. So maybe I should just make a remark here. If you do this in one dimension on the real line, then harmonic functions will just be those functions whose second derivative is 0, right? So that means linear functions, affine linear functions, fx equal to ax plus b, right? And subharmonic functions will be those whose second derivative is greater than or equal to 0. So those would be what? Convex functions, right? And superharmonic functions would be concave functions, right? Okay. Now, in higher dimensions, you can think of subharmonic and superharmonic functions as analogs of convex and concave functions, respectively. So you can define a function on a Riemannian manifold to be convex. There are two equivalent ways of doing this. So suppose the function is a C2 function. Then one way of defining convexity is to say that at each point, the Hessian, so that's a self-adjoint linear map, the Hessian is positive semi-definite at each point. Okay. So what does it mean to say that the Hessian is positive semi-definite at each point? That means the bilinear form Hessian acting on v comma v is greater than or equal to 0. And the Hessian acting on v comma v, that is the second derivative along a geodesic, right? With initial velocity v. So convexity means that the second derivative along geodesics is non-negative, right? In other words, restricted to any geodesic, the function is convex. Okay, so that's a convex function in a Riemannian manifold. So for a convex function, the Hessian is non-negative. So if I take its trace, which is the Laplacian, that will also be non-negative, right? For a non-negative linear self-adjoint linear map, all its eigenvalues are non-negative, right? The Hessian is the trace, it's the sum of the eigenvalues, so that is also non-negative. So convexity implies subharmonic, but the converse is not true, right? So subharmonic is a weaker condition that, so subharmonic, you're asking that the sum of the eigenvalues is non-negative, whereas convex, you're asking that each individual eigenvalue is non-negative. Okay, so is the difference clear?
Yeah. Yes.
Right. Okay, so, but the point is that subharmonic functions have properties analogous to convex functions. Okay. And the idea is that harmonic functions, which are analogs of linear functions, those you can imagine as, in a sense, sandwiched in between convex and concave functions. And similarly, we'll be able to construct harmonic functions using a process where they're sandwiched in between subharmonic and superharmonic functions. So, I mean, let me just give you a little picture. This will be the basis of our construction of harmonic functions later, what's called the Perron method. So this you might have seen in complex analysis. But anyway, it's in one dimension, it's very simple. So you take 2 points, right? And so say an x1 and an x2 And here I have a y1 and a y2. Okay. Now you think of these values y1, y2 as boundary conditions for a function defined on the interval x1, x2, right? So I want to look at functions whose values defined on this interval, whose values at the endpoints are y1 and y2. Now, out of such functions, you know, of course, there's a unique linear function which has these values at the endpoints, right? Okay. So how can I construct this linear function using convex functions? Well, what I can do is I can look at all the class of all convex functions. So let me call this script f is the set of all f from x1, x2 to R, such that f of x1 is y1, or just f of xi is yi, I equals 1, 2, and f is convex. Okay. So what will these functions be like? They will be functions like this, which lie below the line, right? By definition of convexity, the graph of the convex function is going to lie below the line joining these 2 points on the graph, right? So how do I get the linear function? The linear function, let me call this, say, f naught, and these are the convex functions f. How do I get this f naught from these functions f? Any idea? How can I get this linear function from these convex functions?
Sup over all functional values.
Right. So this would be the sup over this family, sup over little f in script f of little f of x. Okay. Is this all right? Yeah.
Yes.
Okay. So what this is the basis of when you generalize this to higher dimensions, say you have a domain in Rn, then to solve what's called the Dirichlet problem, that will be finding a harmonic function with given values on the boundary of the domain. So you fix the boundary conditions like we've done here. Then what will we do? We look at the set of all. So it's not easy to construct the harmonic function directly, but what is always possible is to construct subharmonic functions which have this boundary value, right? So then what we'll look at is the class of subharmonic functions with this boundary value. So it's easy to see that class is non-empty. Okay. So once you have that class of subharmonic functions, then you take the sup over that family of subharmonic functions. That will be our solution to the Dirichlet problem. Okay. So we'll show that under appropriate conditions, first of all, this function will always be harmonic. And secondly, it will achieve the correct boundary values. Okay, so that will be the Perron method for the solution of the Dirichlet problem. Okay, so it's inspired by this simple picture. All right. Is the idea clear?
Yes, sir.
So it's useful to keep in mind the analogy with convex functions. When you think of subharmonic functions, there is a close analogy with convex functions. Okay. All right. So we started talking about harmonic manifolds. So before that, for a general Riemannian manifold, we described some properties of the Jacobian, right? And we computed the Laplacian of the distance function as a logarithmic derivative of the Jacobian in the radial direction. So del J del R divided by J. And then we defined a a harmonic manifold to be a manifold where the Jacobian is a function of R alone. So it doesn't depend on the unit tangent vector V. Okay. And so as examples of this, we saw that Euclidean space or rank 1 symmetric spaces, these are both harmonic manifolds because the stabilizer of any point in the isometric group, it acts transitively on unit tangent vectors. Okay. So using that, you get that the isometry group acts transitively on unit tangent vectors. And using that, it's easy to see that the Jacobian is independent of the tangent vector. It only depends on the radius r. So is that clear? Should I explain this more?
Yes, sir.
Is-
this is clear.
This is okay. Utsav, is this all right?
Yes, sir.
Okay. So
Yeah,
these
you
are,
can-
yeah, sorry, Rudrada, should I explain this? Yeah.
Yeah, we can quickly go over again once.
Sure.
That
Let
will be
me go.
nice. Yeah.
Sure, thanks. Sure. So, okay. So the point is that, so for n equal to Rn or rank 1 symmetric space. Okay. So you let G be the orientation preserving isometry group of M. And so for each point P and M, you have the stabilizer of P. So this is a subgroup of G, and there is a natural action of this on the tangent space at P. Sorry, supposed to. So there's a homomorphism, an injective homomorphism to the special orthogonal group of the tangent space, which just sends a element G in the stabilizer to the derivative of G at P, right? Because G is an isometry which fixes P. The derivative at P acts on the tangent space at P. And because G is an isometry, this linear map is also an isometry. And it is orientation preserving because we're looking at orientation preserving isometries. Okay. So this homomorphism is injective because we've seen this argument before, right? If two isometries, if they fix a point and they have the same derivative at that point, then the isometries are equal. Okay, you do that by looking at geodesics starting from P. So, you know, if this derivative at P is equal to identity, then that means G is going to fix every tangent vector at P. And so therefore, you know, it's going to fix every geodesic starting from P, right? Because this initial tangent vector is fixed. And given this initial tangent vector, there is a unique geodesic with this initial condition, right? So G of gamma is going to be a geodesic with the same initial condition as gamma. So therefore, G of gamma is going to equal gamma. And then once it's an isometry, that means distances from P are preserved. So that means that every point on this geodesic has to be fixed, right? Because this distance is preserved. Okay. So that means this geodesic will be fixed. Okay. And so then since the manifold is complete, then you get that the map will be the identity, right? All these geodesics are going to be fixed pointwise. Okay. And as Orkojit pointed out, it's true also for connected manifolds. You don't need completeness in full generality. You can use a connectedness argument. Okay. You can use a connectedness argument to show that G must be the identity if it fixes a point P and if its derivative at P is identity. So this map is an injective homomorphism to SO n minus 1. Sorry, SON. Okay. Oh. And so, so KP acts on TP1n. G dot V is just DGP of V. And for a rank 1 symmetric space, this action on the unit tangent sphere is transitive. Okay. And also the action of G on M is transitive, right? So this action is transitive. And the action of G on M, this action is transitive. So these two together imply that the action of G on the unit tangent bundle, this is transitive, right? Because so the action is given by the derivative. It's G dot V is dg P of V, where V belongs to TP1M. Yeah. So this action is transitive because you take any two tangent. So let me make this picture a bit bigger. Okay. So here are 2 points P and Q. And I'm taking the unit tangent sphere here. And the unit tangent sphere here. And if I have a V here and a W here, then first of all, I have some element of the isometry group, which maps the point P to the point Q. So that will send this tangent vector V to some tangent vector V prime. And then I apply an element of the stabilizer of Q to send this tangent vector to W, right? Okay, so this action is transitive, right?
Yes.
And from this we get, so let me call this isometry which sends V to W. Let me call this, so say DG at P. Okay. So this is going from where to where? This is going from the unit tangent sphere TP1M to the unit tangent sphere TQ1M. Okay. And now I have the map phi r. So phi r of V is XP RV. Okay. So that's going to send this to a point on the geodesic sphere. Right? This distance is going to be R. Okay. And then I have the isometry G acting here. Okay. So on the right hand side, I will have another map phi r, which is phi r of W is XQ of RW. And this G I can see as going from the sphere of radius R around P to the sphere of radius R around Q. Okay. And this diagram commutes, right? Is that clear? Because this map is sending V to, you take the geodesic with initial condition V and then flow along it for time R. And then I apply the isometry G. So G is going to send this geodesic to another geodesic starting from Q. And the initial condition of this geodesic is going to be given by the value of the derivative of G acting on V, right? And that is the vector W. And so when I go along the right-hand side, this arrow, I'm getting also the geodesic with initial condition W flowing for time R, right? So this diagram commutes, yes? So I have these diffeomorphisms between these spheres. Okay. And now, what is the Jacobian at VR? This is equal to the determinant of d phi r at V, right? And JWR is equal to the determinant of d phi r at W, right? But now, if I take at the points, say V here, and I have my W here, if I take the derivatives of these maps, okay, these are all diffeomorphisms between, there are 4 spheres, and we have these 4 diffeomorphisms such that this diagram commutes. If I take the derivatives of these maps, then again I get a commutative diagram where the derivatives commute. And these 2 horizontal arrows, these are isometries, right? So these 2 derivatives are going to be isometries. So their determinants are going to be 1, right? So by the chain rule, I mean, the product of this determinant and this determinant is equal to the product of this determinant and this determinant. And the horizontal arrows, the determinants are 1. Therefore, the 2 vertical arrows, the determinants are equal. Is this okay?
Yes, sir.
Rudroda, is this all right?
Yeah.
Okay. So this shows that the rank 1 symmetric spaces are harmonic manifolds. So you can see where this fails for higher rank, right? Because the action of the stabilizer is no longer transitive on the unit spheres.
Right.
So that's where it fails. Yeah. Okay.
Right.
So for a harmonic manifold, we already saw that for a general manifold, the volume of the geodesic sphere of radius r, we get by integrating the Jacobian JVR over the unit tangent sphere with respect to the volume measure of the unit tangent sphere. And this JVR, now it doesn't depend on V. So this is just a constant J of R. So this comes out of the integral. And then you just get the integral of, just the Riemannian volume of the unit sphere. So that is just the volume of Sn minus 1, the Euclidean sphere inside Rn, right? Okay. So, so for a harmonic manifold, this Jacobian up to a constant is nothing but the volume of a sphere of radius r. Okay. So geometrically, the Jacobian is just the volume of a sphere of radius r. Okay. Now we can use the Jacobian to construct harmonic functions, certain harmonic functions on a harmonic manifold. So we say that a function f on the manifold minus a point P is radial around the point P if f is constant on geodesic spheres around P. Okay, so you have your point P and you have spheres around P. And your function is constant on each sphere. So that means if I take a geodesic starting from P, then the function is determined by its restriction to this geodesic, right? So then the function becomes a function of just one variable. Okay, so a radial function you can think of as a function on the interval 0, infinity, right? Okay. So if this function is, say, u from 0, infinity to r, then that means the radial function f is going to be of the form u composed with the distance function from P, right? This
Yes.
will be the form of any function which is radial around P. Okay. It's of the form u composed with distance function around P. Okay. Now, so we have f is equal to u composed with distance P for some function. So we proved a change of variables formula, right? For a composition of functions. And we also know what is the Laplacian of the distance function, right? So it was del J del R divided by J, but here J is just a function of R. So the Laplacian of the distance function will be just J prime over J, right? Composed with the distance function. Is this clear? Okay. So this is the Laplacian of the distance function. It's given by the logarithmic derivative of the Jacobian. So notice the Laplacian of the distance function is itself a radial function, right? The Laplacian of the distance function, it is itself a radial function. Okay. I mean, this
That's because the distance function itself is radial, so
well,
Laplacian will preserve that.
yes, but that's only for harmonic manifolds. That's
Okay.
only for harmonic manifolds. So I mean, see, for we had this formula. It is del J del R at VR divided by J of VR. But now, well, this formula, this is, see, this is, what do I mean? What do I mean when I say this formula? When I write this formula, this is Laplacian of the distance function at the point x p of RV. Okay, so so now the point is this right-hand side for a harmonic manifold, this does not depend on V, right? So here V is a unit tangent vector at P. R is positive. So this doesn't depend on V, so this is just J prime R over JR, right? And this XPRV, as V varies over the unit tangent sphere, this varies over the geodesic sphere of radius r. So this means that the Laplacian of any point on the geodesic sphere of radius r is j prime r by jr for all q in the geodesic sphere of radius r. And this is equal to the level set where the distance function is equal to r, right? So that means if on this level set, this Laplacian is equal to j prime over j, then that means in general, the Laplacian I can write as j prime over j composed with the distance function. Okay. Yeah, so for a general Riemannian manifold, it's not true that the Laplacian will preserve radial functions.
Okay.
So yeah, so that is true for harmonic manifolds. So so we can see that when we do this computation, so here's the computation. If we take a radial function f equal to, so it's of the form u composed with the distance function, then the Laplacian of f, this is the Laplacian of u composed with distance function. So we found the formula for this, right? This will be u double prime composed with distance function into the norm of grad dp squared plus u prime composed with distance function into Laplacian of the distance function. And now the first term is okay because this norm of grad dp, we know this is always 1, right? The gradient vector field of the distance function is just the unit normal vector field to the geodesic spheres, right? So this is of norm 1. So this goes away. But this second term, in a general Riemannian manifold, there's no reason why this will be radial again. But for a harmonic manifold, this is again radial. And so then when you add the two terms, you get a radial function, right? You get u double prime plus u prime into j prime over j composed with the distance function. So this tells you that the Laplacian preserves the space of radial functions. Is this okay?
Yeah. Yes.
So in fact, I think if I remember correctly, that is an equivalent condition that a manifold is harmonic if and only if the Laplacian preserves the space of radial functions. And that is if and only if the Laplacian of the distance function is radial. So I think these are equivalent. At least these are necessary conditions is clear, right? The sufficiency, I have to think a bit. So yeah, probably these are also sufficient. Probably this is because yeah, right. I mean, if it preserves the space of radial functions, then this Laplacian of the dp must be radial, right? That is clear. So because I mean, you just take these two terms to the other side, divide by this term, you'll get that the Laplacian of dp. So that's it. And once you know that the Laplacian of dp is radial, I think then it should not be too hard to show that the Jacobian must be independent of v, right? The Jacobian should depend only on, because then you get that this, what is it? This del j, del r by j, this doesn't depend on v, right?
Right.
So when you integrate this, you will get that log j does not depend on v, right? If you integrate this in with respect, you will get log j. You will get that log j doesn't depend on v, and therefore j does not depend on v, right? I think that should be a correct proof. Yes.
So, sir, what is the claim you were saying? Can you just repeat?
The claim is that the manifold is harmonic. So see, we have these three statements. M is harmonic. So this means by definition, the Jacobian doesn't depend on V. The second claim is for all P and M. Laplacian of the distance function is radial. And the third statement is that for all P and M, Laplacian maps, how should I say, the space of radial functions around P to itself. Okay, so we have clearly, we've shown that 1 implies 2, which implies 3, right?
Right.
Now, if we have 3, then 3 also implies 2. That's easy to see, right?
Yes.
Okay, from this formula for the Laplacian of a radial function, you use this formula and you'll see that this term is radial because this norm dp squared is 1. This term is radial, so I take these two to the other side and I divide by this, and so I'll get that Laplacian of dp is radial, right? So 3 implies 2. Okay, let me start another session, right? We're almost out of time. Let's start another session. Right. So M harmonic implies the Laplacian of the distance function is radial. And Laplacian of the distance function is radial implies that radial functions around P map to themselves. And thirdly, radial functions mapping to radial functions. That will imply that the Laplacian of the distance function is radial. Well, that's just because the distance function is radial. So its Laplacian by 3 by hypothesis will be a radial function. So trivially 3 implies 2. The only implication left is 2 implies 1, right? So for 2 implies 1, I think this will be correct. So suppose, so we have the Laplacian of the distance function at say Q. This is, well, okay, let me write it better. So at the point xp of RV, okay, this is equal to del J del R VR divided by J VR. Now, what are we saying? We're saying that this is a radial function, the Laplacian of the distance function. That's our hypothesis, right? So this is some function u of R, right? Okay. So this is for all v in TP1M.
Right.
right?
Hmm.
And R positive. So what does that mean? That means that del J del R divided by J, this is independent of V. It just depends on R, right?
Right.
So that means what? That means if I look at log J of VR, this is equal to integral from 1 to R of del J del R Vs divided by J of Vs ds. This is equal to integral 1 to R U ds. So this does not depend on V, right? Therefore,
Right.
the does not depend on V, right?
Yes.
Okay. So the right hand side is independent of V. Okay.
Yes. Right.
Rudraga, is this okay?
Yeah. Yeah. Okay.
So these should be all equivalent. There's one small point I'm not okay. Well, there's one small point which actually needs to be clarified, but I've read this, I have to check this out. So see, this function of R, a priori this depends on P, right? So what I will get here is that this is independent of V in the unit tangent space at P. That is true. But actually, this should be independent of all V in the whole unit tangent bundle.
Hmm.
So there is a point to clarify there. So what we want is for all V in the whole unit tangent bundle, not just at each point P. Do you see what I mean? This function of P, this function of R, a priori it could depend on P, right? It doesn't have to be the same function of R for each point P.
Right.
So that's one small, but it is true. Nevertheless, I think it's still true. So yeah, so there is a little more work to be done here. It's not immediate. So I'll look this up. There's some more work to be done. But I think this is still true. I think this is still true. So I'll look it up. Okay. Okay. So anyway, we can use this formula, Laplacian of a distance function. Sorry, the Laplacian to construct harmonic radial functions, because f will be harmonic if and only if this function in brackets, which is just a function of one variable, this function is 0. Right? So this is to a second order ODE, a second order linear ODE for a harmonic radial function, u double prime plus u prime into j prime over j equal to 0. Okay.
Right.
And this we can, so the Laplacian, which was a second order differential operator, once you look at it acting on radial functions are functions of one variable. So, and that space of functions of one variable is independent under a second order operator. So naturally that second order operator should turn into a differential operator in one variable, right? Of order 2. So that's what it becomes. The Laplacian becomes this second order differential operator in one variable, u double prime plus u prime into j prime over j, right? So if you like, this is the Laplacian in radial coordinates. So this should be 0. So you get a second order linear ODE now. And this is easy to solve explicitly, right? So one solution is the trivial solution, u equal to a constant. So that will just give you the constant functions, which are of course harmonic and radial. And the other solution is non-trivial. So this is the integral of 1 over j, right? You can see that explicitly you just plug this in, this will solve this equation, okay? All right.
Yes, sir.
So now what does this function look like? Well, as r tends to 0, remember that j, the Jacobian, we saw that it the Jacobian looks like r to the n minus 1 times something converging to 1, right? So if I take 1 over the Jacobian, that will be 1 over r to the n minus 1. So when I integrate that from 1 to r, that is going to converge to minus infinity, because I mean r is less than 1, and the integral is from 1 to r is minus the integral from r to 1. So okay, maybe I should just write this as so we have this solution. We get this radial harmonic function, which is given by this function. U of r is integral from r to 1 of 1 over js ds. Okay. So j of r, this is r to the n minus 1 into 1 plus little o of 1, right? As r tends to 0. So when I integrate, that means that this is going to look like, so here there will be a difference between 2 dimensions and higher dimensions. So in 2 dimensions, this r to the n minus 1, this becomes r. So when I integrate, I get the integral of 1 over r. So this will look like log r, or log 1 over r, right? Plus big O of 1 as r tends to 0. When n is equal to 2. And in higher dimensions, it will look like 1 over a constant times 1 over r to the n minus 2. Right?
Yes.
Okay.
Hmm.
So in either case, you can see that this radial harmonic function, it has a singularity at the origin, right? At the point P. Okay. So this
Yes.
function, this radial harmonic, this blows up at P. Okay. So in fact, this radial harmonic function, this is what we will call the Green's function based at P. Okay. This will be what's called the Green's function based at P. So this is harmonic outside the point P, right? And it has a pole at P. It has a single pole. So there are 2 cases now where you want to look at the behavior of this function as r tends to infinity. So here we got the behavior as r tends to 0, but we can also look at the behavior as r tends to infinity. So in the 2-dimensional case, as r tends to infinity, this is going to tend to minus infinity, right? So in the 2-dimensional case, the function will look like this, right?
Mhm.
Okay, so it tends to plus infinity here near the origin, and it tends to minus infinity near infinity. Okay, this is n equal to 2 case, and n greater than or equal. In general, you can't. Actually, well, okay, no. No. Sorry. This is a well in Euclidean space. In Euclidean space, this would what you get. Okay, so all right. This maybe let me say for Rn. For Rn, what are these radial harmonic functions? So in Rn, the Jacobian is just is the volume of the n sphere, right? Up to a constant. So the Jacobian is just r to the n minus 1 into a constant, right? In Rn. Exactly r to the n minus 1 into a constant in Rn. So in Rn, you'll get exactly these functions, log 1 over r and a constant times 1 over r to the n minus 2. So in Rn, what will happen is the pictures will be different for n equal to 2 and n greater than or equal to 3. Okay. Actually, what happens is, I'm going ahead a bit. If I look at this function gp equal to u composed with gp. So this is the radial harmonic function, right? This is radial harmonic on m minus p. Okay. Then the Laplacian of this function, well, of course, it's 0 outside the point P, but it is not 0 everywhere, in the sense this Laplacian is actually a distribution. It is minus the Dirac delta at P. Okay, in the sense of distributions. And so this Laplacian is, well, it's a measure which is a non-positive measure. Okay, so that means that this function is actually superharmonic. Okay. This function is actually superharmonic because its Laplacian is non-positive. And in the n equal to 2 case, you can see that this function is, of course, not positive everywhere. It tends to minus infinity near infinity. Whereas in the n greater than or equal to 3 case, this is a positive superharmonic function. And it turns out you can, from the viewpoint of potential theory, it's important to classify Riemannian manifolds into two types. Those which have a positive superharmonic function and those which do not. So in fact, in R2, there is no positive superharmonic function on all of R2. All right. Whereas in Rn for n greater than or equal to 3, you do have positive superharmonic functions, these Green's functions. Okay.
So Kingshuk,
Yes.
yeah, so first of all, when you define this superharmonic and subharmonic function, you meant in the sense of distribution, less than equal to 0 and greater than equal to 0, etc.
Right. So there are different ways to define subharmonic and superharmonic. So the first thing is these are allowed to take the values infinity and minus infinity. So what you want is you have to impose a semi-continuity. So either upper semi-continuity or lower semi-continuity, depending whether you're looking at superharmonic or subharmonic functions. And well, the general definition of subharmonic and superharmonic functions, which we'll give, is they are semi-continuous functions which satisfy the following property. So I have a function. So we'll give this definition later in the course. So let me give it. I think for subharmonic functions, you want U is so from your domain D and M to minus infinity. I suppose, yeah, take extended real numbers, and this should be lower semi-continuous. So that means that U of X is less than or equal to lim Uy, y tends to X. And what you want is, if I take any, well, you can take balls or you can take any domain really inside D, say a U. If I have a harmonic function, H harmonic on U, so this is a domain inside D such that U closure is a compact subset of D, okay. And such that H is greater than or equal to U on boundary of capital U, then H is greater than or equal to U on the domain U. So that's why it's called subharmonic, because that means that if on the boundary of a domain your function is less than a harmonic function, then inside that domain it is also less than that harmonic function.
Okay.
Right. So, I mean, for smooth, for a C2 subharmonic function, that will be equivalent to the Laplacian being greater than or equal to 0. And this property, then it follows from the maximum principle, right? You look at U minus H. So that is subharmonic and less than or equal to 0 on the boundary. Therefore, it should be less than or equal to 0 inside. Right? From the maximum principle for subharmonic functions. So, but I mean, that in, let's say in Rn, I mean, this is a consequence of the normal definition of subharmonic in terms of Laplacian greater than or equal to 0 and the maximum principle. But in the general setting, we take this as the definition. We take this property as the definition, because it gives a more flexible class. These functions don't have to be smooth. They don't have to be C2. And, you know, then you can see that the maximum of two subharmonic functions will also be subharmonic. And of course, typically when you take a maximum, right, then it's not going to be smooth. You see, there'll be corners where the derivative doesn't exist. When I take the maximum, right? So say I have these two, they're like convex functions. So if I take the maximum, I'll get this function, right? Which is not smooth here. But it will be subharmonic according to this definition. So this is more flexible, and this is what we need for the Perron method. We need to consider, it's useful to be able to consider subharmonic functions which are not smooth. So hence this definition. So this Green's function satisfies. So similarly for superharmonic functions, you have a similar definition. You just reverse the signs of these inequalities, right? So this Green's function is superharmonic in that sense. In this, according to this definition, but I think it is also equivalent to saying that, yeah, I mean, if you're, let's say, subharmonic in this sense, it is true that the distributional Laplacian is actually a measure, and it is a positive measure.
Okay.
And so, but that I have to look it up. I don't know the proof of that. Yeah. But I think that is true that what you're asking, that the general definition of subharmonic would be that either you can give in terms of this definition using comparison with harmonic functions, or you can say the distributional Laplacian is a positive measure. I think these two are equivalent. But I have to look this up. I'm not sure. Yeah. 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 So the Laplacian will be a measure for superharmonic and subharmonic functions. So in general, I mean, for a general continuous or semi-continuous function, the Laplacian doesn't have to be a signed measure, right? I mean, it could be worse, something worse, a distribution which is worse than a measure. So, but I think for subharmonic and superharmonic functions, you have some regularity of the distributional Laplacian. It can't be too bad. It's at worst, it's a measure. At worst, it's a measure. So, I think this is true. I have to look it up. Yeah, I'm not sure. I have to look it up. But this definition of subharmonic using comparison with harmonic functions, we will use this definition. Yeah, we will use this definition later in the course. Yeah. So sorry, any other questions or comments, Rudra?
No, so you said that any radial harmonic function
Right.
will have a singularity always at that point, right? About which it is radial.
That is true because if you look at this second order ODE, then these are the two linearly independent solutions. So any solution will be a linear combination of these two, right? So as soon as it has a, as soon as this solution appears, it will have a singularity. Yeah. The other solution is just the constant. So yeah.
Right.
So that's true. Any radial harmonic function will have to, it will have to have a singularity. You're right. Yes, that's right. That's that's right. Yeah. Okay. So, all right. So now we make a definition, which is a special case of a more general definition, which I won't do. So we say that the harmonic manifold M is parabolic if this integral from 1 to infinity of 1 over j diverges, and hyperbolic otherwise. Okay. So you see in examples, if you take M equal to Rn, then constant times the Jacobian is just the volume of the R sphere, that is R to the n minus 1. So the Jacobian is just R to the n minus 1. And so Rn is parabolic if n equal to 2 and hyperbolic if n greater than or equal to 3. And for a rank 1 symmetric space, the sectional curvature is less than or equal to -1. Then we saw by the Jacobi field comparison theorems, the Jacobian is going to be greater than or equal to sin HR to the n minus 1. So this grows exponentially. So the integral of 1 over j is going to be finite, right? Because that decays exponentially. So what does this mean, this parabolic and hyperbolic? What it means is that if M is hyperbolic, then this this radial harmonic function with the singularity at the origin, this converges to a finite limit as r tends to infinity, right? And so therefore, if I add a constant, then I will get this radial harmonic function will be positive everywhere on the manifold, right? Whereas, and so it will give me, well, what I'm saying is it will give me a positive superharmonic function. Whereas in the parabolic case, it turns out there are no positive superharmonic functions. So that's the difference between this parabolic and hyperbolic. Okay, it's the basically existence of positive superharmonic functions or their non-existence. All right. See, well, you know that there are no positive harmonic functions in R2, right? On all of R2, there are no positive harmonic functions, right? Yes, Rudrada Utsav,
Yes, yes.
right?
By
It's a
Lewis.
classical. But actually, that is also true for Rn, right? In Rn, there is no positive harmonic function on all of Rn. That's also true in higher dimensions. But the difference is that for higher dimensions, you do have positive superharmonic functions. You do have positive superharmonic functions. You don't have positive harmonic functions, but you have positive superharmonic functions for n greater than or equal to 3. So there's a difference between n equal to 2 and n equal to 3. So yeah, so one has to be a bit careful that existence of superharmonic functions does not imply existence of positive harmonic functions. That's not true.
Non-constant, you mean? Yeah.
Non-constant, of course. Yeah,
Yeah, it can be shown. Yeah,
right,
there is no.
right.
Mm.
So, I mean, but the thing is, for n greater than or equal to 3, you do have positive superharmonic functions.
Okay.
Right.
Okay.
This Green's function, the Green's function will be the positive superharmonic. So, which is just this 1 over r to the n minus 2. This function will be positive superharmonic,
Okay.
but it's not harmonic, of course. Yeah, on all of r. Okay.
So what does the potential theoretic notion of having a positive superharmonic function reflect about the manifold geometrically?
Well, okay, so yeah. Okay, look, I did read up about this, but I may make some slightly incorrect statements. I will have to look at this again. I think in terms of the Brownian motion, the parabolic means the Brownian motion is recurrent, and hyperbolic means the Brownian motion is transient. So transient means with probability 1, every sample path of the Brownian motion goes to infinity. That means it leaves every compact eventually. Okay. So that is a transient Brownian motion. So in the hyperbolic space, what happens is the Brownian motion is transient, and in R2, the Brownian motion is recurrent. So that means it will keep coming back into any neighborhood of a given point. It will actually return to any neighborhood infinitely often with probability 1. But in R3, the Brownian motion is transient. So with probability 1, it will escape to infinity. So at least in terms of Brownian motion, you have this interpretation of parabolic versus hyperbolic. It is basically the recurrence or transience of the Brownian motion. But yeah, if you're asking for a more geometric interpretation, then, well, you can see here that in some sense, I suppose it's related to volume growth and being negatively curved in some sense, right? So you can see these negative, actually any manifold where the curvature is less strictly negative, let's say less than equal to -1, will be hyperbolic, right? Because the Jacobian will grow exponentially by a volume comparison.
Right.
Okay. And yeah, we'll do this later. In fact, what is a positive superharmonic function? You can take 1 second. Let me just think for a second. So right. Yeah, so what Anderson and Shun do, they take exponential of the distance function, e to the minus delta d rho dp. So if I take the Laplacian of this, right, so I have u double prime composed with dp. So u double prime will give me a delta squared into right, so it's u double prime plus u prime. So u prime gives me a minus delta into Laplacian of the distance function. Okay. Okay. Right. So this, you can see this Laplacian is going to be less than or equal to 0. If I take delta small, this delta squared is going to be small compared to this minus delta term here, right? And this, by the Hessian comparison, this is going to be greater. This is going to be greater than or equal to a constant. So this Laplacian. So this will be a positive superharmonic function. And so therefore the manifold will be hyperbolic. I'm not assuming harmonic here, that the manifold is harmonic. So yeah. I'm not assuming the manifold is harmonic. So for delta small, this will be a positive superharmonic function. So right. So this will show that this is positive. Yeah. Right. You see, I mean, if I do the same thing in Rn, what happens in a negatively curved manifold? We saw that this Laplacian of the distance function. So, I mean, this is trace of the Hessian, right? And the Hessian is bounded above and below by two positive constants, right? As R tends to infinity. So this stays bounded below. Okay, this stays bounded below as r tends to infinity. In negative curvature, if the curvature is less than or equal to minus a squared. So whereas in Rn, this Laplacian goes to 0. Okay, in Rn, it's just the logarithmic derivative j prime by j. This is just n minus 1 over r, right? This goes to 0 as r tends to infinity, right?
Yes.
Okay, so in Rn for large R, this term is going to go to 0. So then this Laplacian will become positive for large R. You see,
Yes.
this term is going to go to 0. This term is constant, so this will become positive for large R. Whereas in negative curvature, this is bounded below by a fixed constant. Okay, and so this term will dominate this term, and this Laplacian will be negative. Is that okay?
Yes, sir.
Yeah.
So yeah, I mean, so negatively curved manifolds will be hyperbolic. That is, but I mean, of course, it's a sufficient condition. Of course, it's not necessary, but it's a sufficient condition. Negative curvature will imply hyperbolic. Yeah. So parabolic in particular will satisfy the Liouville property. There are no bounded harmonic functions on a parabolic manifold, right? Because I mean, if you have a bounded harmonic function, you just add a constant, it will become a positive superharmonic function, right? So yeah, parabolic manifolds satisfy the Liouville property.
Except R2, what can be other examples of parabolic?
So non-negative Ricci curvature. Yeah. So some sort of non-negative curvature will lead to parabolicity. So non-negative Ricci curvature, I think, is the okay. So right. So Utsav, I think yes. So non-negative Ricci curvature is not enough. That implies the volume growth is polynomial. And right, so then there are theorems. I think Rudrada, you would know about this, right? Lee and Yao, that if the volume growth is, I mean the space of harmonic functions is finite dimensional, right? With dimension bounded by constant times the polynomial volume growth, right? So something like that. Right?
There are several papers on this. Yeah.
On this line, yeah. I don't know this. I don't know.
What
this,
about a compact manifold? Will it be always parabolic?
Yes. Compact manifold, yes. That's by the maximum principle. Because a superharmonic function will attain its minimum and therefore it will be constant. Yeah. That is by the maximum principle. Yeah. Compact manifold is always parabolic. So, I mean, these definitions are meaningful for non-compact manifolds. So,
Right.
for compact manifold, that's a trivial case, really. Yeah, sorry, I'll have to look up the papers, which Rudradan will know better than me. These papers.
No, not that, but yeah, I mean, there are other classifications, right? Depending on volume growth, as you were saying.
Yeah, I think, I mean, this show the space of harmonic functions is finite dimensional. Is that correct? Yeah, I think. Yeah, I think something like that.
Right. Harmonic functions are fine, yeah.
Finite dimension.
Finite dimensional subspace, yes.
Right. And the dimension is controlled, like if the volume growth is like r to the power n, then the dimension is something like a constant times n, something like that, I think. Right. Something like that. I'm not sure, but I'll have to look it up.
Yes. Yeah.
What is true is that non-negative Ricci curvature implies, by the Bishop volume comparison theorem, it implies the volume growth is polynomial. That is true. So, and if the volume growth is, I think, yeah, this is a theorem of Yau. If the volume growth is like R squared and non-negative Ricci curvature, then you have the Liouville property. The bounded harmonic functions are constant. That I think is true. I think I've seen this in a paper of Yau. This is an early theorem of Yau. Yeah. So like the R2 case, basically, if the volume growth is quadratic, then you have the Liouville property. Okay, I'll look up these because I'm not familiar with these papers. I usually think about negative curvature and not the other direction, which is non-negative curvature. Yeah. But Utsav, yeah, to answer your question, roughly, I mean, geometrically, parabolic corresponds to non-negative curvature, and hyperbolic corresponds to negative curvature, roughly speaking.
Okay, sir.
Yeah, but it's not an exact correspondence, right? I mean, there's no necessary and sufficient condition or anything like that. In terms of geometry, there's no necessary and sufficient condition.
But R2 has both the Rn has both the behaviors.
Correct. Exactly.
Yeah,
Yes.
that's strange.
Right, exactly. Rn has both the behaviors. Exactly. Yeah. Right. Yeah. So, which tells you that curvature alone is not enough, right? Because I mean, Rn, the curvature is always 0. So yeah. So curvature is not enough to decide this problem. Yeah. Okay. All right. So okay. So now we define the Green's function. So this will be very important for us for a harmonic manifold. So we define this to be so minus 1 over Cn integral from 1 to R of 1 over the Jacobian. Well, this is just a function of R. If M is parabolic, we define this. And if M is hyperbolic, we take the integral from R to infinity. And then we define the Green's function with pole at P. So this will be a radial harmonic function around P. G sub P is this function G composed with the distance function at P. Okay. So note that GP is harmonic on M minus P. GP tends to plus infinity as Q tends to P. And the behavior as Q tends to P is like big O of log 1 over R if n equal to 2, and big O of 1 over R to the n minus 2 if n is greater than or equal to 3. So what is the importance of this behavior near the pole? The importance is, if I look at the integral of the Green's function over the sphere of radius R, this will tend to 0 as R tends to 0. Why is that? Because the total mass of the sphere of radius R looks like R to the n minus 1, right? As R tends to 0, it looks like a constant times R to the n minus 1. And here, R to the n minus 1 times either of these functions, this converges to 0, right? As R tends to 0. Okay. Is that all right? Yeah.
Yes.
Okay. I mean, you just take out the sup norm of GP from this integral times the volume of the R sphere. So the sup norm is bounded by a constant times this 1 over R to the n minus 2. And then you multiply by the volume, which is bounded by a constant times R to the n minus 1. So you get a constant times R, so that goes to 0. Okay. And if it's log 1 over R, then that's even smaller. So log 1 over R times R to the n minus 1, that also goes to 0, right? Okay. So this integral of the Green's function over a geodesic sphere of radius R, this goes to 0. So why do we need this? Because now we can prove, well, the following lemma. that if phi is a function which is continuous in a neighborhood of P, then the integral over the geodesic sphere of radius r of the inner product of I'm missing a grad here. This should be grad GP inner product with n. Sorry, this is a typo. So let me just write it correctly. So that times phi d sigma r, this converges to minus phi of P as r tends to 0. So sorry about that. I'll write the correct statement here. So the correct statement is integral over geodesic sphere of radius r inner product grad GP with the normal vector into phi d sigma r. This converges to minus phi of P as r tends to 0. Okay. So this in Rn you can see this directly. So by a computation example in Rn, this GP is a constant times 1 over norm P minus Q to the n minus 2. So in terms of the r coordinate, it's just constant times 1 over r to the n minus 2. And this inner product of grad GP with the normal vector to the sphere is the radial vector field, right? So this inner product is just the radial derivative of G, right? This is just del G del R, right? In polar coordinates. So del G del R, this is going to be minus n minus 2 over Cn into 1 over r to the n minus 1, right? And then when I integrate this d sigma r in polar coordinates will be r to the n minus 1 d theta, right? Where d theta is the volume form on the unit sphere. The Jacobian is just r to the n minus 1, right? So when I integrate, I'll get this r to the n minus 1 will cancel with this r to the n minus 1, right? So the integral over the sphere of radius r this will be minus whatever, minus a constant. So I'll just write a constant C over r to the n minus 1 into phi d sigma r. So this becomes so minus a constant times integral over the unit tangent sphere TP1, so Rn, okay, over the unit sphere, the 1 over r to the n minus 1 and phi, and then you have the Jacobian, right? J of r d lambda p, right? Yeah. This is the change of variables formula to go from the geodesic sphere to the unit tangent sphere. The Jacobian of the change of variables is just the Jacobian J of r, and this J of r is a constant times. So well, there'll be a 1 over c here, and there'll be a c times r to the n minus 1 here. So these will cancel. This will cancel this, and this c will cancel with this. And so you'll get the integral of phi over a small geodesic sphere, and by continuity, this will converge to minus phi of p. Is that okay? So that's the computation in Rn. Okay. And a similar computation will work in any Riemannian manifold, well, in any harmonic manifold. So here's the computation. So this inner product of grad g with n, this is g prime r, right? The g is a radial function, so this is going to be g prime r, which is by definition minus 1 over Cn into 1 over j of r. Okay. So we get this integral is minus 1 over Cn into 1 over jr into, so phi is continuous, so I can write phi on this small sphere as phi of p plus something which is little o of 1. And then I use the change of variables. This integral over the geodesic sphere becomes an integral over the unit tangent sphere. I have to multiply by the Jacobian of the change of variables, which is just j of r, d lambda p. So this 1 over jr cancels with this jr, right? And I get this minus 1 over Cn. And then I have the integral of a constant phi p with respect to the volume measure of the sphere. So that gives me the volume of the n minus 1 sphere, which is this constant Cn. Okay. And this little o of 1, this term goes to 0, right? This integral goes to 0. So I'll just get, this converges to minus 1 over Cn into phi of p, which is minus phi of p, okay, as r tends to 0. Is this okay? Yeah?
Yeah.
Yes.
Okay, so now using this, we can prove what I was saying earlier, that the distributional Laplacian of the Green's function is minus the Dirac mass at p. Okay. So this means that actually the integral of gp times the Laplacian of any CC infinity function phi is equal to minus phi p. Okay. All right. Okay, so this is the meaning of this statement, that, I mean, the distributional Laplacian acting on a test function phi is defined to be this integral. Okay. So this integral is equal to minus phi p, and minus phi p is just the Dirac distribution acting on phi, right? Okay. So to prove this, we're going to use Green's formula. Okay, so what we do is, let me draw you a picture. So we have a point P, and we have phi, which is a CC infinity function. So what we're going to do is first take a large ball which contains the support of phi. And then we take a small ball. Okay, so we have an annulus. So this is of radius little r, and this is of radius capital R. And then we're going to, so we look at the domain D, which is the annulus bounded by these two, and we apply Green's formula to this domain, right? So Green's formula, remember, was integral over D, U Laplacian V minus V Laplacian U d vol is equal to integral over boundary D of U inner product grad V normal vector minus V inner product grad U normal vector ds. Okay. So we're going to apply this with the functions, the Green's function and the test function phi, right? So this integral over the boundary will give us two integrals. one over the big sphere and one over the small sphere, right? Now the integral over the big sphere, what will happen? So there, if u is my test function, u is 0 on the big sphere, and also grad u is 0 on the big sphere. So the integral over the big sphere will vanish, right? So you'll just get the integral over the small sphere, okay? Right? Okay, and this integral over the domain D, if I take, so u is equal to phi in CC infinity, my test function, and v is equal to the Green's function, g sub p, okay, then the Green's function is harmonic on this whole annulus, right? Because the only singularity is at p, which is outside the annulus. So this Laplacian v is 0. So in this integral, this Laplacian v term will vanish, right? So what will remain is just this minus integral of v Laplacian u. So that is the integral I'm looking at, gp Laplacian phi, right? Okay. Right?
Yes.
So let me call this domain D sub R. And then the idea is you let R tend to 0, okay? And you'll compute and you'll see that using the previous lemma, this integral will converge to minus phi of p. So let's do that computation. Okay, this is the idea. All right. So we apply Green's formula to this annulus. D sub R is the large ball of radius capital R minus the small ball of radius little r. Okay. So by Green's formula, this first of all, the integral over this D sub R of gp Laplacian phi, I can write this as the integral of gp Laplacian phi minus phi Laplacian gp, because the Laplacian of gp is 0 on this domain, on this annulus. And now I apply Green's formula. So this is integral over the boundary of the annulus, gp grad phi inner product n minus phi grad gp inner product n. And as we observed, the integral over the big sphere is 0, because both grad phi and phi are 0 on the big sphere. So this just becomes, so notice that if I orient the boundary correctly, I'll get the integral over the big sphere minus the integral over the small sphere, all right? Okay, so I'll get big sphere minus small sphere. So here, the integral over the small sphere will come with a minus sign. Okay, so there's a minus sign here. And then what do I have? gp grad phi n minus phi grad gp n. Okay. Now, what about the first term? So the first term, because phi is a smooth function, this grad phi is bounded in a neighborhood of p, right? So this term is bounded. Okay, this inner product grad phi n is bounded near p, and this integral of gp over the sphere of radius r, this we already saw, this goes to 0 as r tends to 0, right? Yeah, this we've already seen. So this first term here is going to go to 0, right? Is that clear? Yeah, this is bounded, and the integral of gp over d sigma r goes to 0, right? This we already saw, right?
Yes.
So this first term is going to go to 0. And then I have a minus and a minus, that gives me a plus. So then I get integral of phi grad gpn, that by the previous lemma converges to minus phi p. Okay. Right, that's the previous lemma that we proved. And so therefore, and then as r tends to 0, the left-hand side, which is the integral of the annulus, that converges to the integral of the whole domain, because gp is a locally integrable function, right? it only has one singularity. At that singularity, it is locally integrable, right? This singularity, like 1 over r to the n minus 2, this is integrable, right? This is integrable over a ball, right? You just, in a ball, in polar coordinates, the Jacobian will look like r to the n minus 1. That into 1 over r to the n minus 2, that will be integrable, right? So GP is locally integrable, all right? The singularity is integrable. So therefore, this integral over the annulus will converge to the integral over the whole domain as r tends to 0. Okay. Is this all right?
Yes,
Yes, sir.
yes.
So we get that we have this distributional solution to the Laplace equation, right? So this is often called a fundamental solution to the Laplacian, right? Because in Rn, once you have this, then you can construct any solution to the Laplace equation by convolution, right? Right. In Rn, what would you do if you want to solve? Say Laplacian f equal to h, right? And you have that Laplacian of g is equal to the Dirac, let's say at 0, right? Then you write h as h is equal to h convolved with the Dirac, right? And so the Laplacian of f convolved with g this would be the Laplacian of h convolved with g. Sorry. The Laplacian of h convolved with g. This would be h convolved with the Laplacian of g. And this would be h convolved with the Dirac, and this would be h. Right? Okay.
Yes.
Right. So this is how you solve Laplace's equation. Once you have a fundamental solution, then by convolution you can get the general solution. Right. So in a harmonic manifold or in a general Riemannian manifold also, really, with the Green's function you can solve the Laplace equation. The only thing is, instead of a convolution, it will be an integral operator. So I mean, you have that, if I define a function of two variables, g of p cube is g sub p of q, right? Where g sub p is the harmonic function with a pole at p, the Green's function. So Laplacian gp is minus delta p. So then formally, how are you supposed to do this? So if I take a linear combination of, say, summation sum over p belongs to some finite set S, say alpha p gp, then this will be minus some alpha p delta p. And linear combinations of Diracs, these are dense in the space of distributions. So these will converge to any function you want, any locally integrable function h. Okay. So h you're writing as a limit of these Diracs. Okay. In other words, that means the integral of any f times h is the limit of sums minus alpha p f of p. Okay, and so this Sum is basically what this is. This converges to, this is Laplacian of integral over n minus h of p gp. Right. So this is equal to so you'll get this this solution as an integral operator. This is just a formal computation I'm doing here, but you can justify this. Does this make sense? Yeah, this is your solution. It's minus HP G of P cube d vol P. Yeah. D vol of P. Right. So we know that in the Q variable, this is harmonic, right? So when I integrate over P, this is going to be sorry, I mean, well, no, this Laplacian is Dirac. So right. So when I integrate, and formally, if you differentiate this, you'll get Laplacian of this is equal to H. Okay. So you can justify this. Yeah. This will be
Green's function.
right. So you can solve the Laplace equation using an integral. I mean, it's like a convolution, right? In Rn, this becomes this G of PQ is just 1 over P norm of P minus Q to the n minus 2. So this becomes a convolution, right? In Rn. But in a manifold, you don't have a linear structure. So it's just an integral operator. It's just an integral. Is this okay? Yeah.
Yeah.
Okay. So this is why the Green's function is important to solve the classification. Okay. So we can now use the Green's function also to prove the mean value property for harmonic manifolds. Okay. So if U is harmonic on an open set in M, and we take any closed ball of radius capital R in U, then the value of U at the center of the ball is the integral of well, U over a geodesic sphere, but what's important is the measure with respect to which you integrate over the sphere. So the measure is the following: you take you integrate over the unit tangent sphere U of X RV with respect to d lambda p into 1 over Cn. So this d lambda p into 1 over Cn, this is a probability measure. Okay, this Cn is nothing but the volume of the unit tangent sphere. Okay, so this d lambda p divided by this volume, this is a probability measure. So therefore, this is an average value. Okay, this is a mean value. And this mean value, I should say, this is the same as the mean value with respect to the surface area measure of the geodesic sphere. So maybe I should just clarify that. That's true for a harmonic manifold. So for a harmonic manifold, this integral over the geodesic sphere of, say, U of Q d sigma R of Q. So this d sigma, this is the Riemannian volume measure of the geodesic sphere. So here I can do the usual change of variables, right? I put Q equal to X R V, okay, where V is a unit tangent vector. So this becomes an integral over, oh, and wait, I want a mean value, so I divide by the the volume of the sphere. Okay, so that's the integral, just d sigma r cube. Okay, so I make this change of variable in both these integrals. So what happens? So this becomes u of x rv, and then I get the Jacobian, right? So in a harmonic manifold, it only depends on r. So this is just j of r, right? And then I get d lambda p of v, right? And below, what do I get? Below I get integral over TP1m j of r d lambda pv. Okay. So this j of r doesn't depend on v. Therefore, it cancels, right, from both these integrals, right?
Hmm.
And so what remains below? The integral below is just the volume of the unit sphere, which is the constant Cn, right? So this becomes the integral over Tp1m of u of x p rv d lambda pv over Cn. Is this okay? Yeah.
Yes.
All right. So that's so this is really the mean value with respect to surface area measure of the geodesic sphere. Okay. Is the same as this integral. Okay. So I've just written it directly like this. Okay. All right. Okay. So will we have time to finish this? Maybe not. So let me, there's just 4 minutes left. I suppose we could do it, but it's just a computation. You want to use Green's formula again. But now you, instead of applying it with the function u and the function gp, you apply it to a function h, which is gp minus gp of capital R. Why we subtract this constant is because then on the boundary of the big ball, this function vanishes on the boundary of the big ball. Okay. So that gives some simplification when you apply Green's formula. Yeah. So let me do this next time, all right, on Friday. Yeah, then we can do it slowly in detail without rushing. So any other comments now before we finish in the last few minutes, or questions?
Yeah.
So this mean value property again is this is particular to harmonic manifolds. Maybe I should, well, I'll remark that there is a version of the mean value property for general Riemannian manifolds, so not necessarily harmonic. But then what happens is the integral with respect to which you compute the mean value, the measure with respect to which you compute the mean value, that is not the surface area measure divided by volume. Rather, you get some abstract probability measure on the boundary of the ball, such that if you have any harmonic function on the closed ball, then the value at the center
Or harmonic measure.
yeah, the harmonic measure. So the integral over the boundary of the ball with respect to harmonic measure, say d mu p comma r, So this is a measure on the boundary of the ball, a probability measure. This gives H of P for all A harmonic on the closed ball. So what is special for harmonic manifolds is that in a harmonic manifold, this harmonic measure is actually equal to the Riemannian surface area measure.
It's a characterization of harmonic manifold, is it?
I think so. I think so. I have to check again, but I think that is a characterization. You're right. I think so. Yeah. 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 Right. Yeah. So in a general Riemannian manifold, what will happen is the harmonic measure will be absolutely continuous with respect to the surface area measure, but not equal to it. I mean, the Radon-Nikodym derivative will actually be the normal derivative of the Green's function. So like in Rn, yeah. So the Green's function of the ball, not of the whole space. Green's function of the ball.
Yes.
So, okay, so we'll continue on Friday then. So
Okay.
yeah, okay. See you then. Okay.
See.